All right, I'm here. I am 32 minutes late. I am so sorry. I apologize, but I was in I was on a previous meeting with my fellows from the Acadia organization, from the Acadia Association, the Association for Computer Aided Design in Architecture, and we are we're planning the conference that is going to happen in November this year, and we have a lot of things to decide, and it's like we're very much into the height of, so meetings just typically take long. It's just how what it is. So I'm sorry it took me this long, but I'm back. I'm ready to go. I've had my coffee already, and we are. What are we doing today? What are we doing this afternoon? We are doing lists of data. Um, is that what we're doing? Let me let me look at my notes. Yes. So we saw. Hey, Andres. Thank you for waiting, man. I'm sorry. I'm sorry. I'm sorry. I'm sorry. This took so long. So what are we doing today? We are going to be doing lists. We're going to be doing hands-on exercises using lists. So, and for that, we're actually going to start with oh, here, yes. So, okay, Nylan, yes, thank you, sir. So what are we going to do? We're going to do 3 exercises. We're going to do a Virendel. That's correct, right? Okay, so we are going to where is now where here. There you go. Virendel beam. Can you hear me? Yes, you can hear me. How do you pronounce this? Can you? Oh. Arthur Virendel. Let me.
Virendil. Virendil.
Virendil. Virendil. Ooh.
Virendil truss.
Nah.
Virendil truss.
Virendil. Well, I'm not going to know how to pronounce this, so it doesn't matter. Virendil does. Trust. Okay. So, and the way we are going to do that. Images. Tools, usage right, Creative Commons. Virendil. Virendil Trust. All right, so we're going to do the following. We are going to, sorry, you should not be seeing this. We're going to do a Virendel truss. We're going to do a Pratt truss, right? No? A Pratt truss. We're going to do something like that, and we're going to do images, tools, usage rights. We're going to do a Pratt truss, something like that. For example, yes, we're going to do one of these. We're going to do one of these, and then what are we going to do? What else are we going to do? We're going to do a Warren truss, which is going to be something like this, and then Yes, so we're going to do something like this. All right. So Pratt, and Vierendeel. Vierendeel. All right. And these are going to be very useful exercises because they involve data manipulation and they involve having like a set of lists, a set of points, and moving them around and removing some, adding others. So it's actually a pretty good exercise. And then after that, so we're going to do a Warren cross, and then after that, we're going to do some kind of like triangulated facade and then triangulated surface. Ooh, that's going to be quite something actually. All right, so those are going to be list exercises. Okay, so let's start. So we're going to do we're going to do a Vierendeel truss. So how am I going to start? So I will start with the introduction, which I will record by the end. And then that's going to be me showing 2 points and how the Vierendeel truss goes between them. And then I am not going to explain there, but I'm going to explain. I'm going to explain here when I start with the sketches, and I'm going to explain how we want to do that. And the fact that instead of calculating a long line, we're going to use small segments. So we're going to imagine that we are structural engineers and that the model that we're generating is for some kind of structural analysis software. That's going to be important to do. That's going to be important. Okay, so, and when we do that, so how do I start? I would like to start by saying that the process that we're going to follow is we're going to start with 2 points. Wait, how are we going to do this? Okay, so how are we going to do this? So I'm going to start with the intro and then I'll start here and I will break down the problem. So the problem that we want to do, the problem is we typically have 2 supports, right? For example, we have 2 supports, 1 support here and 1 support here. And what we want to do is we want to create some kind of structure that goes like this and then like this, and where the beams, the chords are horizontal. That was a terrible diagram. Like this, like this, like this, like this, and like this. So the process that we're going to follow is, and the typical thing that we want to control is we want to control, for example, this distance. When to control this distance, we want to control the number. So we want to control, all right, so that's going to be L. So we want to control L, we want to control the number of spans. So we want to control the number of spans, and we want to control the depth. And it's just that the depth is typically referred to as L divided by a factor, and the factor is going to be what we want to control. Okay, so that's going to be the the starting points, the talking points. And then once we have that, we can say, well, probably the process that we want to follow is that we're going to create a line, something like that. And then we're going to subdivide this line into however many segments. Then the next process that we're going to do is we're going to move these points here. And then on a last process, we will make we will do the vertical elements. The vertical elements. Where is the name for the vertical elements? Oh. Up. Yeah. A top chord, a bottom chord, and a bracing between the top and the bottom. Chord. Okay. Okay. Nope. Element trust. No. Nope. That's not what I want. That's not what I want. All right. So I'm going to. Oh, actually, you were not looking at my screen. Sorry. Okay, so I'm going to have those. And then once I reach this point, I can probably start talking about how we're going to do this. And I probably want to say that that once I have this, what I would like to do is I would like to create first the vertical elements. That's going to be one thing. And then after that, because I would like to send this to a structural calculation analysis, I would want to create the other elements as single elements. So this is what I would like to talk about. I think this is the story that I want to tell for the introduction. So let's see how that goes. Hmm. All right, so let's get started. Can I say that this is probably one of my favorite topics because I also teach structures and I was a structural consultant for many years before I became a computational designer. So designing structures parametrically is one of my favorite things in the world, probably. So let's start to think about the problem. So the problem that we're trying to solve here is to create a structural element parametrically. And when it comes to trusses, to spatial arrangements of bars, very typically we start off by thinking that we need to cover a particular span, right? And the particular span that we want to cover, we need to cover it in an efficient way. So you might be familiar with Virendell trusses, which are this particular kind of trusses that are made up of square spans, each one of them having rigid connections on the nodes. We're not going to get into why that's important or why that is structurally sound, but they have certain advantages and they have to be made in a particular way. So for these exercises, for this one and the ones coming down on the series, coming further down in the series, I would like for us to consider that we're going to put our shoes we're going to put ourselves in the shoes of structural engineers, and then what we're trying to do here perhaps it's not going to be so much oriented towards visualization, but it's going to be perhaps more oriented towards structural analysis. So we're going to be designing parametric structures that we're going to imagine are going to go into a structural analysis software or maybe some plugin in Grasshopper that does that. And a lot of the decisions that we're going to make are going to be geared towards that goal. So what are we going to do? Well, the first thing that we're going to do is we're going to define which parameters are the ones that are going to drive our truss. And obviously, arguably the most important one is going to be the length of the truss. In our case, for this definition, we're not going to work exactly with the length. We're going to have the two nodes. So we're going to have the beginning and the end, the two supports as the input data. So we're going to have 2 points in Rhino that we're going to move around. And then we will try to design a truss that spans through those two supports. And therefore the length between supports will be implicit depending on where the supports are in 3D space. Another parameter that we will want to control is how many spans this beam will have, which will be an integer, like something that we can control numerically. And very typically, a super important parameter as well of trusses is what's called the depth, which is the technical term in structures that we use to refer to the height of the truss. Now, one thing that I would like to highlight here is that because we are doing this more from a structural engineering point of view, typically in structures, we don't really work with the absolute value of the depth of a beam or the depth of a truss. What we typically do is that we set that value as a factor of the overall length of the beam. So there are some good hands-on rules. So there are some good rules of thumb about certain beams with certain materials should be somewhere between the range of the length divided by 12 or the length divided by 16. Those are typically like good rules of thumbs about dimensions. So it will be that value, the factor that we divide the length by, that I will want to control as a parameter, and therefore the depth, which will be whatever value. That will also be very useful because if we ever move the two supports farther apart, the proportion of the truss will remain the same. The truss will not just get thinner as we go longer. So that would be very useful. And then what we would like to do is we would probably like to follow a process that will look something like this. We will take our two supports, create a line between them, divide the line into however many spans we have defined parametrically, then takes those points, like a distance that is controlled by the depth of the truss. And then, and this is the important part, we will want to design the bars that will be part of this truss as linear elements. So we will literally create lines that will be those bars for the truss, and that we will send to the imagined structural software analysis. We're not doing that here, but this is just hypothetical. So we will do, for example, we will design the vertical bars of this truss, but most importantly, the horizontal chords, so all the horizontal bars, instead of being one single continuous bar like the red line that I drew before, they're actually going to be single spans of linear elements. So if we have 6 spans, we will need 6 chords joining this point here with this point here. Whoa, that was a really big one. So this point here with this point here will need to be one line. This point here with this point here need to be another line. This point here and this point here will need to be another line. And this is very important in structural calculations, because if we have one continuous line and we have a bar here, since the longer line doesn't have a node here, this bar will be considered by the structural software to be free, to not be attached to the longer bar, and therefore our calculations will fail. So that's why when designing geometry for structural and software, for structural engineering analysis, it is very important that the elements are segments that are always starting and ending in nodes. It's a really important thing. And that is the reason why this particular exercise will be interesting, because creating this bar, this line like this, will be super easy. Creating a collection of lines like this or like this will take some data manipulation and some list management. And that's why this is the first exercise in the series of designing a few different trusses. Okay? So before we get into the data manipulation part, let's start with the basics. Let's do the supports, let's do the points, and let's do the vertical bars, and then we can address the problem of the horizontal chords. Let's take a look at how to do that in Grasshopper. Alrighty, so let's go back to Grass. So actually, I'm going to, if you allow me, I'm going to take a 30-second bio break, because I've been sitting here since 9 a.m. So I need to go to the restroom. I'll be right back. Thank you. Hold on 1 minute, huh? All right, I'm back. Rolando, analytical models. Yes, exactly. Okie dokie. So let's get started. Okay, so I'm going to copy and paste this too. And then I'm going to say the length. And number of spans is going to be number of spans. And then this is going to be the number slider is going to be the factor. So that's going to be, for example, 20. And we're going to set it at 12. And we probably don't need that many depth factor. Okay. So there's going to be a long slider, and yes. So that's going to be it. And I'm going to copy this. Inputs. Okay, so I think we can probably start. And then, I'm going to save this as, what am I going to save this? Vierendeel. Oh my god, I am super clumsy today. Vierendeel truss, and then here I'm also going to save this as Vierendeel truss. Okay. All right. And what else do I need to do? What else do I need to do? I think we should be good with this, right? Okay, so let's start then. Let's start then. So I've taken the liberty of creating 2 points here in Rhino that I will use as supports for my truss. And then I have created some empty boxes here that I'm going to load with 1 point here. I'm going to set another point here. And then I have 2 sliders. One is an integer for the number of spans for the truss. And another one is going to be the depth factor. Remember, we're going to divide the length. We're going to divide the length of the beam by some factor. And that is what's going to be the parameter. And that factor will give us the depth of the beam. So then the first few steps are going to be super easy. And also, I don't know if we have seen before, but also naming the inputs, even if they are empty boxes, is typically a very nice thing to do. So you can right click on a parameter box and then just rewrite here, for example, start support. And then if you click on the paint bucket, then this parameter will get that name that you have given it. And here, the same, and support. And if I hit the paint bucket, now they have their names. And I'm going to dock them to the right-hand side because you know that I like things aligned and well ordered, etc. And then we have them as well. So the first thing that I would like to do is, as per our diagram, I'm going to create a line between the 2 supports, divide it in points, and move those points down, and then create the vertical bars. We're going to do that very fast because we already know how to do these things. So I'm going to double click and create a line between 2 points. That's going to be the start support and the end support. And then I'm going to take that line and I'm going to subdivide it in an equal amount of length segments. So that's going to be this one. So this is going to be the curve, and then spans is going to be this number. So for example, if I go down to 2 spans, I have 3 points. So that is correct. Okay. So this many spans here, and then K is split segments, and I don't need to care about that. And then the last thing that I would like to do is I will need to take all those points and move them down in C a control distance. How much? That is going to be the depth of the beam. But the depth of the beam, I need to find that in relation to the length between the supports, which is the span, and the factor that I have set. So what I'm going to do is I'm going to go to curves analysis to find to measure the length of a curve. So I'm going to place that here, and I'm going to place a panel, and you're going to see that the panel tells me that this is 8.4 units long, whatever that is. I'm going to divide that by division. What is division? I'm going to divide that by the factor, and that will give me a number, for example 0.70. Okay, and then after that what I can do is I can move all those points down in the z direction a control amount. How much? That depth that I have just calculated here. So I'm going to say I'm going to create a unit z vector that I'm going to multiply by minus oops, so I'm going to negate, I'm going to make this number negative. You see, I should have used an expression component here right now. Let me just use it, why not? So I keep always saying I'm going to do, this should be minus length divided by the factor, and then this should be length, and this should be the factor. And then I have length here, I have factor here, and I think we are good now, no? Length invalid expected parentheses instead of, I think this is just wait, so let me just change the name. Sometimes length is a protected name for expression, so maybe length was a function. Yes, so there was a function called length. Returns the magnitude of a vector or the number of characters in a string. Yes, so it looks like length was the name of a function, so I was using it as a variable and it was getting confused. So this is going to be now minus blah blah blah, which if I multiply by an unit z vector, it gives me a vector in the z direction that is pointing down. So if I now move all these points a controlled amount down, I will have the, you see, and I'm going to do something like a factor of 6, for example, so that it's a little squarish in a way. Okay, and this way, you see, if I move the point farther away, you see the depth adjusts proportionally, which is kind of nice, and it's a very good thing in the logic of structural design. So I have this, and then what I'm going to do is I'm going to do something that will be very useful very soon, which is I have my points, the nodes on the top chords, I have them here. So I'm actually going to, just to make sure that I know where things are very clearly, I'm going to add another empty point parameter. This is something that I like doing a lot as well here. And I'm going to pass these points here, and I'm going to rename this top nodes. All right. And then here I'm going to copy and paste this, and I'm going to rename this bottom nodes. Okay. These boxes, when you pass data through them, they don't really do anything to the data, but it's a really good practice to label things so that we make sure that we know this is important data, I want to put a name on it, and so that when my definitions grow really large, I know where things are and I can point to them really easily. So this is a really good practice. It's a really good thing to do. And just for the sake of clarity also, let me plug in here a panel, and let me plug in here another panel just to see what is going on here. Okay, so I have those and I have those. Okie dokie. So I have now the nodes on top of my curve. I'm going to hide this line as well. And then the first thing that I'm going to do is I'm going to draw the vertical bars. Vertical bars are going to be super easy because it's just going to be joining the family of points from the top nodes with the bottom nodes. And you can see that now I get 7 lines, which are all the points on top with all the points in the bottom. And I would like to remind all of us that this is happening because the line component is doing what's called a matching operation. because it has two inputs and each one of them is a list. What it's doing is it's taking the first point of this list with the first point of the second list. It's taking the second point of the second list with the second point of the second list, the third point with the third point, etc. And that is each one of the lines that the component is generating. So if we give it two lists with 7 elements each, it will create lines between each pair of order points from those lists. And that is something very important to highlight because it will become very important very soon when we start working or trying to design the chords of our truss. Shall we take a look at how to do that? Okay. And so what we're going to do is how am I going to explain this? I'm going to explain that hmm, 0, 1, 2, 3, 4, 5, and 6. And what I want to do is I want to create bars that are like this. Now, and actually, and what I just got here was from the bottom, 1, 2, 3, 4, 5, 6. So what the component was doing was it was taking 0, 1, 2, 3, 4, 5, and 6, and then it was taking 0, 1, 2, 3, 4, and 5, and 6, and it was creating nodes between them. And then here I'm going to say, and we created this. Nope. Here we created this, and this, and this, and this. Okay. Okay, so that's one thing. Now, I'm going to turn this, so that's how I'm going to explain the first part. Now, I would like to turn everything off except for that. And then I'm going to have to explain that what I want to do now is I want to create this, 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 and this. So in a way, what I want to do is I want to take the same list of points, which is going to be 0, 1, 2, 3, 4, 5. Oops. I'm going to take 0, 1, 2, 3, 4, 5, and 6. And I have another list here, which is 0, 1, 2, 3, 4, 5, and 6. So in a way, what I want to do is I need to wait. No. So I am going to okay. Okay. Forget it. Okay. So nope. So in a sense, what I want to do is I now want to join this one with this one, this one with this one, and this one with this one, this one with this one, this one with this one, and this one with this one. And I would like to, on top of that, get rid of this one. I don't need to make that explicit. So it turns out that that is not possible. Actually, turns out that that is not possible. Turns out that that is not possible. And that what I need to do is I need to come up with a way of saying I'm going to create two new lists. One is going to be what, and the other one is going to be 0, 1, 2, 3, 4, and 5. And then after that, all the other elements, I don't care about that. So in order to do that, I will need to then say, I need to take all these points and create one group, which is going to be 0, 1, 2, 3, 4, and 5. And then I'm going to create another group, which is going to be this one here, which is going to be 0, 1, 2, 3, 4, and 5. And once I have those, then I can join them together, and then boom, kaboom, boom, kaboom. Okay. Okay, so let's see if I can explain this in a way that makes sense. Okay, before we actually start describing how we're going to do the chords, let's take a closer look at what have we done for the vertical bars. And remember, what we did was we had a collection of points that were the nodes on top of the truss, and then we had a second list of points which were the points on the bottom of the nodes. So we have two different lists of vertices. And what we did was we joined them with vertical bars. So in a way, we did this because what we did was we took the two lists and we used a component to define lines that were joining the first element with the first element, the second element with the second element, the third element with the third element, etc., etc. So the diagram of elements is we have a list with 7 elements, we have another list, the blue one, with 7 elements, and because both have the same amount of elements, by default, the line component joins them one by one, doing pairs. Okay? So that is the basics of how we have done the vertical bars. Now, the problem here is going to be a little difficult, a little different, because what we want to do now is instead of working with two separate lists of vertices like we had before, we will be working with only one list of points. And then what we will try to do is we will try to join those points with lines that are joining the first one with the second one with the third one, consecutively, etc., etc. So if we were to look at this problem from the perspective of how can we work with that list of data so that we correctly match the vertices that we want to be the start points and the end points of every line, then the problem will probably look something like this. We have the same list of vertices, the same list of points, all of them sorted one after the other. But instead of joining in one to one, like we did before, what we want to do now is we want to do something where we join the first one with the second one. So element with index number 0 and element with index number 1. Then element with index number 1 and element with index number 2. Index 2 and index 3. So we want to join them in a way that is not one to one as they are ordered in the list right now. So how could we do that? Well, if we were writing actual computer code, every programming language has ways of taking a list and then selecting particular elements. We could do for loops and we could do iterators. It would actually be much easier. However, in grasshopper terms, we don't really have a way of telling grasshopper to match things in different order than the one by one basis that we have seen before. So in grasshopper terms, the way we actually circle around this problem is by creating or modifying or reshaping the list of elements so that when they are matched one to one, they actually matched in that order that we want them to match. So in this case, because we know that the first element always matches with the first element and the second with the second of two lists, then what we need to do is we need to create two new lists where the elements are somehow moved around so that they match this logic. How would that look like? That would look something like this. Imagine we have that collection of top nodes. What we can do is we can create a second collection, a second list that is missing the last element. And then what we can do is also in parallel, we can create another list that is missing the first element. And therefore, remember, all the indices will rearrange because they always have to start by 0. And then if we create these two new lists and then we match them together, now because they all have one element missing, the last one and the first one, then when we match them one by one, the first one will match with the second one of the old list, which is now the first one. I don't know if you see that. This one, oops, I cannot draw. This one here will match with this one, which is now the first one after we remove this one. And the second with the second, and the third with the third, and the fourth with the fourth, etc. The idea is we create these two new lists, missing the last element and missing the first element, and as they reorganize, then now the nodes are in the order that we want them to match with each other. So this is, and then we forget after that about the previous nodes. We don't need them anymore, really. So in numerical terms or in graphical terms, this would look something like this. We would have the full collection of lists, the full list of nodes on the top, and then what we can do is we can create a new list that is missing the last one. And then at the same time, we can also create a new list that is missing the first one. And then as we have that, then joining this element with this element, this element with this element, this element with this element, etc., 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 will give us this line here, this line here. I'm making a mess here, but you see where I'm going with this, right? So this is the core of doing list manipulation for the sake of matching things correctly, at least in grasshopper terms. Let's see how could we do that in grasshopper. Okay, let's go back to grasshopper. Now, I'm going to use the point component. I'm going to use the point component to see them. And then am I going to use shift or am I going to use split? I'm going to use split because I think it's a little, shift is not so much for beginners. And then I will use perhaps shift in further tutorials down the line. So I'm going to start with split. For the sake of clarity, I'm going to draw the indices of the points with the point list component and giving it like a little bit of a bigger size here. Oh, that's a lot. So to make sure, I'm going to keep this point list visualizer very handy. This is super handy when I'm doing data manipulation. Okay, so I'm going to keep this handy so that I can see. And then what I'm going to do is, first of all, let me turn this off. Let me turn this off. So first thing I'm going to do is I'm going to create the first list of points, which is the same vertical nodes, the same nodes on the top without the last element. The way we have several ways about doing that, but remember that it's going to be under sets and the list category. And we could use shift list like I explained before, but that's a little more advanced or perhaps more confused. So I'm going to start with split list, okay? The first one that I'm going to do is I'm going to start with split list. And remember that what I need to do is I need to give I need to tell the split list component, which is the index where we are start cutting out from. And then what I would like to do is I would like to cut out from this one and then just keep these ones here. So that's going to be list, and index is going to be whatever. So for example, let me start with a slider. Let me start with a slider here. And then I'm going to keep all of these here. Oops, sorry. What is, oh, sorry. I don't want, oh no, I'm doing it. Sorry, I'm doing it on the list. Sorry, on the top nodes. I need to do it on the top nodes. So I'm going to do that here. And then you can see now that if I set 6 as the number that I'm going to be using for the splitting, what's coming out of A is going to be the same list of points without the last one. And what's coming out of B is the last point, which I'm just simply not going to use. Okay? So then, but obviously, this is not great practice. This is just for testing. But because if I now were to increment the amount of spans, well, you can see that this definition will fail. But it turns out that the 6 is the number that I need to start cutting from, which means that I can either, to make this parametrically, I can either say that the number of spans is the number from which I need to start cutting. And therefore, if I ever increase the number of spans, I'm always going to be retrieving everything but the last point. So that's one way to go. The other way to go is just using the list length, okay? What if to measure how many elements are in the list of top nodes. So that will give me the number 8. And then to that, I can just subtract subtraction. To that, I can just subtract the number 2. And that will also give me where do I need to cut out. Oh, actually, sorry, it's the number 1. Okay, so the list minus 1 unit. So whatever is easier for you. I think in this case, because we do have the number of spans as a parameter, we can use that directly, and we can save ourselves a little bit of computation. So that's going to be one thing. Okay, so here, just to make sure that I'm visualizing this, remember I had all the nodes here, all the top nodes, and here, coming out of A, I have a family of lists which is the same points except for the last one. Now, what I would like to do is I would like to also create another list, which is going to be all the points, like in here. I'm going to be creating this one. So what I need to do is I want to create all the points. I want to create a list that has all the points except for the first one. I don't want this one here. So what I'm going to do is I'm going to use a very similar technique. I'm going to split the list, but hold on one second. Hi, hello. Come on in. Oh. All right. Can you do this one and this one here? Okay. Thank you. All right. Oops. Sorry. Okay. So where I was here. 1 second. So yes, so I'm going to split the list, but this time, because I want to remove the first one, what I'm going to set is here with the panel, I'm going to set number 0 as the index that I'm chopping by. And you can see that this, actually, no, it should be number 1. So number 1 makes the first element go on its own list, and then it gives me a second list, which is all the elements except for the first one. And I can see that very clearly if I plug it in here. You can see how I have a new family of points, which is all the points except for the first one. So I have, let's make sure that we can visualize this real well. So I have these points, all the points except for the first one. And here I have all the points except for the last one. So it's a little overlapped, but you can kind of see where they are. So it looks a little bit like this. And therefore, the only thing that I need to do now is I need to join them with a line component. So what I'm going to do is line between 2 points, and then between the first family, which is all the points except for the last one, and the second list, which is all the points except for the first one. And what's interesting about this is that visually in Rhino, they look like a straight line, which is normal. However, internally, they are a collection of 7 lines, all of them with the same length. Is 7 lines a Does this make sense? Yes, because I had 7 spans. 6 spans will now give me 6 lines, which also makes sense. All right. So, so that was great. Um, so yeah, so that's what we needed for the top chords. Now for the bottom ones, literally is going to be just copy pasting because the logic is the exact same one. So before I do that, I'm going to make sure that here I say this is going to be the vertical, this is going to be the vertical bars, and then here I am going to group this, and then I'm going to make sure that these are the top chords, and then I'm going to copy and paste this, but instead of using the top notes, I'm going to use the bottom notes, and I'm going to plug those in here, plug those in here, and then kaboom. Now I have the same thing. I have a list of lines that are the bottom chords. So, ta-da! So I think that's it. Just for the sake of visual flavor, I could do something, for example, like putting a pipe around them. Just be careful because pipes are actually fairly expensive to render Rhino-wise. So they can look something like this. And then I can make the radius a little smaller. And I can make the ends be rounded by plugging here the number 2, for example, right? And I can now make this look more like a beam or not. I don't really know, but this is just for visual flavor. In reality, I don't really need that. So so yeah, so that was creating a Vierendeel truss. And of course, now as I move these points around, the Vierendeel truss adapts. And if I do less spans, more spans, if I do the depth factor, everything adapts correspondingly. So this is cool, I think. Okay. All right. So this was a simple exercise creating a Vierendeel truss. It was a good example on how to do simple list manipulation so that we do controlled data matching. Now, I think with this, I would like to move on to more elaborate examples, like other kinds of trusses, like the Warren truss, the Pratt truss, etc., and to further show examples of how we can do data matching and data operations. So follow me up on that one on the next videos coming up after in this series. And in the meantime, if you liked what you saw, maybe you want to consider subscribing or liking this video, etc., etc., and all those things. Thank you very much. See you on the next video. Okay, so how am I going to talk about this? Vierendeel truss. Vierendeel truss. There's no good example. Which example do I want to use? Perhaps this one? That one is not very nice. Maybe I want to do that one. something like that, perhaps. Okay. I don't need to show this. Okay, well, maybe I do. I don't know. Hi, this is Jose Luis, and welcome to a new video in this series, Introduction to Parametric Modeling. And in this next series of hands-on exercises, what I would like to do is I would like to model a set of spatial trusses, because these are really good examples of data matching and data manipulation that we can do at the list level. And the first one that I would like to do is I would like to try a Vierendeel truss, which looks something like this. And if you look it up on Wikipedia or whatever, you can see that Vierendeel trusses are actually a very popular model for some certain infrastructures, bridges, and even from some building structures, because they don't have diagonals and they rely on the joints being rigid elements. So we don't really care about that here, but I would like to make an exercise where we model two supports and then where we create a Vierendeel truss that spans between the two supports with a controlled amount of spans, of course, and with a controlled amount of depth factor. And even though we are going to model like a surface to give it some visual entity, at the end of the day, what we will actually really care about is about the diagram of the lines that join the two span supports, because we're going to imagine that we're going to be structural engineers and that what we need is the structural model to send it to some software analysis or some kind of calculation environment. So we will export this model to okay. All right. I'm going to start over again because I did not like that. So, okay, I'm going to start over again. Mhm. Hi, this is Jose Luis, and welcome to a new video in this series, Introduction to Parametric Modeling. In the next few videos, I would like to do some hands-on exercises to practice data manipulation and data matching. And for that, I thought that doing some spatial trusses would be a good exercise. So we're going to start with the simplest one that I can think of, which is a Vierendeel truss, which looks something like this. Vierendeel trusses are very common structures for certain kinds of bridges and for certain kinds of building structures, because since they rely on the joints being rigid joints, not allowing any rotation, then they can get away without having diagonals, which for many people is a really nice aesthetic thing, and you can also pass things through, etc., even though it makes the elements be typically a bit bulkier. But here for us, that doesn't really matter. What matters is that we will be interested in creating a parametric model that, given two supports, so one point on one end and the other point on one end, can create a parametric truss beam, Vierendeel truss beam between them. And of course, we're going to control the amount of spans, we're going to control the depth factor, etc., etc. And even though we will have this surface, this pipe surface around them, what we will actually be interested in is in the wireframe diagram representation of this beam. Because we're going to imagine that this truss, that we're going to be structural engineers for this work, and that we're designing parametric structures that will need to go to some structural analysis software, finite element analysis, whatever. So we're actually only interested at this point in the wireframes, but with certain conditions that I will explain very soon. So without further ado, let's do the first round of trusses, which is going to be the Vierendeel truss. Something that I forgot to add to the previous video was baking all of this stuff. And then showing it as how they are individual lines. I want to do that. Sorry. And I forgot to add to the previous video. I actually want to bake these lines to show you how things work out. So typically something that I like doing is that when I finish a complex definition, I like to set up some boxes, so some empty parameter components with the actual target or the output or the goal of my definition. So for this, I'm going to create some line empty parameter box, and I'm going to plug in here the vertical bars, the top bars, and the bottom bars. So I'm going to end up with a component that contains all the information that I was trying to generate with this definition. And then this will be the one that I will use for baking. So I'm going to right click here, I'm going to bake, and I'm going to click on grouping. I'm actually not going to click on grouping anything. Okay, so I'm not going to group anything, and I'm going to close grasshopper. And you can see that now what I got was this spatial Vierendeel truss with each one of the vertical bars. But at the same time, you can see how each one of the top chords is individual and it goes between nodes. And each one of these is also an individual line segment that joins the nearby nodes. So this is great. This is perfect. It's super clean. And it would be a wonderful wireframe CAD model to send to a software, to a structural engineer, a structural calculation software. Okay, so yes, so this was really good. Good job. All right. I'm going to delete this before I forget because I don't want to save that. And so that's going to be here. I'm going to open Grasshopper. And this is going to be, okay. All right. And then I'm going to group this here as top nodes. This is going to be bottom nodes. Nope. This is going to be bottom nodes. Oops. And I know, honey, I do want to do the shift list method, but I think I'm going to do that in the upcoming exercises, which I probably have to do tomorrow because I need to go. I know I started late, but I also need to go. I have another meeting starting in 10 minutes. So okay, so I have 10 minutes to do Q&A on social. So if anyone has any question, we can take a look at that right now, or anything you want to comment. I'm going to say afternoon 25.5. Does anyone have questions or things you want to address? Or comments or just chitty chatter, anything? I'm happy to comment things. Yes, Yasin, please go ahead. Will you talk about third-party plugins later? Like what would you like me to talk about? Like do tutorials on other plugins or talk about the idea of plugins in general? Andres, news on the Acadia workshops? Yes, the Acadia workshops have been announced. And by announced, I mean there is an open call for people to submit proposals for teaching workshops. So we have a rolling application. I think the deadline is June 18th, and you can propose to teach a workshop at Acadia, and then if you get accepted, then you will be teaching that workshop the second week of September. So this year the workshops are separate from the main conference. We're going to do them in September, and then the main conference will be in November. We thought that could be a good idea. Since we're all virtual, it doesn't really matter when those happen. And September, people are a bit more free to engage in these kind of activities. So we're going to, so there's an open call right now to submit proposals to teach a workshop. Once those proposals go through, we will make a curated selection of those workshops and we will announce them at some point in July. And then somewhere in July and August, we will open up for registration, and then people will be able to sign up for workshops and participate in, again, it's the first week of the second week of September. Let me actually copy a link. There's a link here to the call. If you want to participate or teach a workshop, you can go there. Yasin, I'm not sure what you mean about volumetric ones. And again, I'm not sure if you mean me teaching other plugins or talking about plugins or writing our own plugins. That I will definitely talk about very soon. Nylon, is this the method followed for complex structural optimization or for plugins like Caramba? So plugins like Caramba, what they do is that they typically take a structure that is made up of line elements, and once you put some forces and some stuff on top of that, they do structural calculations. Then if you want to optimize that structure, then if the structure has been parametrically designed, then you can do things such as Galapagos and change the parameters and the sizes of the elements and optimize them structurally, and that is a really cool thing to do. But yes, this kind of operations is the start to structural optimization, if you will. I think you can hear a lot of background noise. Is that right? Okay, well, I think I'm going to have to go. Thank you very much for being here. I will see you. There's no live stream tomorrow morning. We have a live stream tomorrow in the afternoon. Okay, so I'll see you in the afternoon and I will continue doing these exercises of parametric structural design. Okay, thanks a lot. See you tomorrow. Bye-bye.